Hello everyone, this is Divya, working as a technical department in St. Peter's Engineering College. So in this lecture, I want to revise about full wave rectifier. So first of all, what is meant by full wave rectifier? Full wave rectifier is a type of rectifier which converts the alternating current or voltage into pulsating direct current or voltage during both half cycles of the applied input voltage. When we are compared to the half wave rectifier, in the half wave rectifier we can generate the output only either for the positive half wave or negative half wave. But here in the full wave rectifier we can obtain the output for both the positive wave and negative wave of the input. So we can convert the alternating current or voltage into a pulsating direct current. What is meant by rectifier? The device which is converting the alternating pulse into direct pulse is called as rectifier. So, the device which converts the alternating current or voltage into pulsating direct current or voltage during both the half cycles of the applied input voltage is called as full wave rectifier. And coming to the types of full wave rectifier, the full wave rectifiers can be divided into two types. Those are the first one is center taper full wave rectifier and the second one is full wave bridge rectifier. Coming to the center taper full wave rectifier, here we have to consider two diodes only. So these two diodes are connected across a transformer that is a center taper transformer. For this transformer in the primary there exists single winding that means only two terminals, but for the secondary winding there exist three terminals. Those are A, B and C. So in between AC the same power is conducting and in between DC also the same amount of power is conducting here. So even for the half cycle, that means even for positive half cycle, this AC will connect D1. That means the positive pulse is connecting across D1. That means current flows to D1 when D1 so that the D1 is conducted. And for the odd cycle, that means for the negative half cycle, D2 will conduct so that the current flows to D2. If the D1 is conducted in the positive half cycle, the current passes in this direction. That means here D1 will act as a closed path and the current passes through the load resistor RL so that the output appears across the load resistor RL. If the D2 is conducted for the negative half cycle, then D2 acts as a closed path here so that the current will pass here through the external load. So here this is the resultant output voltage waveform. For the positive wave conduction and for the negative wave conduction also, the output voltage is same. Why? Because the current flowing through the RL direction is same for the two cycles. So here for the positive pulse also the output is positive and for the negative also the output is positive. So here T is the time taken to conduct the thyristor and VDC is the output pulsating voltage, V maximum is the maximum voltage. So this is the zero voltage and this is the maximum voltage. And coming to the results, so this is the input which you are giving to the center taper transformer. So that here if I consider the positive peak, then D1 will be conducting. If I consider the negative peak, then D2 will conduct here. So here this is the output conduction of the D1. For the D1, the positive peak only the output comes in this period only 0 to 5. And again the D1 conducts in 2 pi to 3 pi time period. For the negative cycles, the D2 will conduct. The time period is pi to 2 pi radians and 3 pi to 4 pi radians. So by combining the output, finally we can draw the output voltage across the rectifier, that means load resistance is. So this is the output voltage by conducting the output voltage which is produced due to the conduction of D1 and D2 combining itself. So these are the formulas obtained by using the waveforms. The average voltage formula is 2V maximum divided by pi, where V maximum is the maximum secondary voltage and RMS value is nothing but root mean square value. So IRMS is equal to IM divided by root 2, that is 1.414. PIV means peak inverse voltage. That means peak to peak voltage. So here the peak inverse voltage is 2VN. And coming to the next one, that is full wave bridge rectifier. This is the second type of full wave rectifier. First one is the full wave center tap rectifier, and second one is the full wave bridge rectifier. Why it is called as bridge rectifier? Here the construction looks like a bridge here. So here I used a total four diodes. That means D1, D2, D3, and D4. So which is connected across a load. The input is here. We are taking the input as AC. We have to obtain the output as DC. So I can explain this in two ways. So here I consider for the positive half cycle. That means here if the input is positive, then the diodes D1 and D2 will conduct. That means if the input is positive, the current will enter in this way. D1 is conducting, load current is passing, and then V2 is obvious and path goes like this. That means a closed path should be formed to pass a current. So this is the operation for the positive half cycle, and coming to the negative half cycle, we have to consider the diodes D3 and D4 which are conducting each other. That means if you are considering the negative half cycle, the negative current flows in this direction as shown here. So here from this direction the current flows here, and from here the current enters into the load. From the load the current passes to the D4, and the current enters again the source, so that the total cycle completes here. That means closed path is forming here. So the output will appear across the load. This is the operation of the full wave bridge rectifier for the negative half cycle. And coming to the ripple, if the output voltage of the rectifier is not completely a DC voltage, if there exists any periodic variations, then it can be treated as a ripple. If you observe the output of a center tap bridge rectifier, this is the output, right? So this is the AC waveform, and this is also called as AC waveform. Why? Because this is also a alternating waveform with respect to time. But what is our final aim? We have to obtain a pulsating DC. So how you can obtain the pulsating DC? That means if you cut it, the AC, that means top of the line, that is a constant one, then we can obtain the pulsating DC. So this can be treated as a ripple. So this ripple can be reduced by using filter circuit at the output of the rectifier. So the ripple can be considered by using a factor that is called as ripple factor, and that is indicated by gamma. Gamma is equal to under root of Vrms divided by Vdc whole square minus 1. So here Vrms is nothing but the RMS voltage of the rectifier, and Vdc is nothing but the output DC voltage. So this is the formula for the ripple factor. So the full wave rectifier with smoothing capacitor, that means to neglect the ripple, that means to achieve a pure DC output, we have to connect a smoothing capacitor across the rectifier. So here this is the full wave bridge rectifier. I connected a capacitor across the full wave bridge rectifier as shown in this circuit diagram. So what will happen is the output which is passing through the load will appear across the capacitor. So this capacitor will filter the harmonics in the output current so that you can achieve the pure pulsating DC here. So if the AC is converted into pure pulsating DC, then that is called as a economical rectifier. So this economical rectifier will convert the AC into pure pulsating DC. So here the capacitor charges for this period and capacitor discharges for this period. And total this is called as ripple. This ripple can be reduced by using a smoothing capacitor. I use the capacitor. You can use a inductor or else inductor capacitor circuit as the smoothing filter here. So this is about the full wave